Good afternoon. My name is John Sawyer. I am the Executive Director of the Mid-Atlantic Quantum Alliance, and it is my pleasure to welcome so many of you today to today's fireside chat, and especially to our panelists, Dr. Bill Phillips and Dr. Laurie Locascio. Please note that today's session is being recorded, so if you don't want to participate in a recording, please leave now. We've gotten a lot of interest in this topic, so we'd love to get to know you just a little bit better, and I'm going to put up a little poll while we get started. All right, so hopefully everyone is seeing that, and I will continue. So in terms of logistics, I will introduce our panelists in just a moment, but first I just want to make sure that everyone is familiar with the mechanics for the event. We have a couple of folks helping to run the show, so please hide all of the non-video participants. This fireside chat is designed to be a dynamic and informative event, so we'd love to address audience questions. Please just submit questions through the Q&A function throughout the event, and we will try to weave them into the discussion. If possible, we will also reach out to some of the questioners to see if they would like to ask the question directly. So you'll just need to raise your hand once we contact you, and then you should be able to go on video and ask the question directly. Now to give a quick introduction to the Mid-Atlantic Quantum Alliance, or MQA. We are on the cusp of a second quantum revolution. The first is what gave us transistors, GPS, MRIs, and a number of other transformative technologies. Quantum is growing to become a multi-billion-dollar industry that will disrupt many traditional industries and sectors. We're still in a relatively early stage for a lot of quantum technologies, but there is clearly a major need to bring together the technologists with the end users and the potential customers, as well as to start to grow the talent pipeline for this growing industry. The Mid-Atlantic, especially around the nation's capital, has one of the greatest concentrations of quantum expertise and capabilities in the world. The MQA serves as a forum to bring this expertise together to both raise awareness of the second quantum revolution and to forge a common vision for building a diverse, vibrant, cohesive, collaborative quantum ecosystem in the region. This will help to lead the nation and the world in this exciting field. The MQA was formally launched in January and has been rapidly expanding since. Our membership currently includes 7 universities, 4 government and government-affiliated labs, 5 Fortune 500 companies, and 3 startups. The MQA is driving quantum innovation through research collaborations between our members, creating new opportunities for preparing a diverse workforce, and connecting entrepreneurs and innovators with potential customers. Today's talk is the first in the MQA series of virtual events to help make the second quantum revolution more accessible to the broader community. Building on today's topic on the basics of quantum science, we will then delve more deeply into specific technologies and applications, especially around quantum computing, quantum sensing, and quantum communications. The next one will actually be this Friday afternoon and provide an industry perspective about where quantum computing is going. For more information about this and other events as they are announced, please visit the MQA website at mqa.umd.edu. I would now like to introduce Dr. Laurie Locascio, the Vice President of Research for the University of Maryland. Laurie?
Yeah, thank you, John, and thank you for joining us. Thank you all. I'm Laurie Locascio, Vice President for Research at the University of Maryland. And let me see, I have this poll sitting in front of me. Does everybody else, am I supposed to share the results, John?
I just did.
Okay, great.
So everyone can see, we have a number of—
I want to make sure everybody could see the results. So as John highlighted, there's a lot of buzz around quantum technologies and the exciting opportunities they unlock. And at the same time, quantum mechanics is pretty counterintuitive to most people. So the purpose of today's event is to help people understand what quantum science is without requiring a background in physics, and what it enables that make quantum technologies so different from the technologies that we're used to today. So to help guide us on this journey, it's just truly my pleasure to introduce Dr. William Phillips. Phil is a National Institute of Standards and Technology, or NIST Fellow, where he's worked since 1978. He's also a distinguished university and College Park professor at the University of Maryland, with appointments in the Department of Physics, the Joint Quantum Institute, JQI, which is an entity between NIST and University of Maryland, and the Institute for Physical Sciences and Technology. In 1997, Dr. Phillips was the co-recipient of the Nobel Prize in Physics for development of methods to cool and trap atoms with laser light. And he shared the honor with Stephen Chu of Stanford University and Claude Cohen-Tanuji of the École Normale Supérieure in Paris, France. Their work combined to create some of the most important technologies of modern atomic physics, which thousands of researchers worldwide employ today for a wide variety of applications. Dr. Phillips received his BS in 1970 from Juniata College and his PhD from MIT. He's a fellow of the American Physical Society, a fellow and honorary member of the Optical Society of America, and a member of the National Academy of Sciences. So first, I just wanted to welcome Bill and thank him for joining us today.
Well, it's great to be with you, to see you again, if only virtually, Laurie. I look forward to when we can sit together in your office and have tea as we've done in the past, but this will have to do for the moment.
I do too. I really look forward to that. So this is going to be a fun talk for me. So before we jump into the discussion about what quantum is and what quantum can do, I first have a couple of questions that I have been wanting to ask you for a while, and I'm sure the audience will like to hear this as well. So what is it really like to win a Nobel Prize? And did you have a eureka moment?
Well, okay, so let's talk about the eureka moment for a moment. We didn't really have a eureka moment, and I don't know whether that much of science is done with eureka moments. For us, it was more like a eureka several months. Probably the thing that our group is most known for is the fact that we discovered, somewhat accidentally, that it was possible to cool things to much lower temperatures than what people had thought possible. And when I'm talking about low temperatures, it's really the lowest temperatures that anybody has achieved for anything anywhere in the universe, as far as we know. Much, much colder than the temperature of outer space. We get things down to nanokelvins, within a billionth of a degree of absolute zero, whereas outer space has a temperature determined by the microwave background radiation that's about 3 degrees. So we get down to less than 1/billionth of the temperature of outer space. But the point was that we were observing something where the temperature was lower than what the theory said was possible. So we thought, we've made a mistake. And we spent several months trying to prove that we'd made a mistake. And when we exhausted all of the ways we could of trying to show that we made a mistake, we had to accept that we'd actually discovered something new. So it was only little by little that it dawned on us that we had done something important. So it was a eureka couple of months.
Can you talk a little bit about winning the Nobel Prize and what that has led to?
It was really quite a surprise to me, because the Nobel Prize can only be given to 3 people. And so many people had contributed so much to the development of laser cooling and trapping that I imagined that there would never be a Nobel Prize for it, even though the subject matter I thought deserved a Nobel Prize. I just didn't see how it was possible to figure out whom to honor in this way. But the Nobel Committee figured it out, and I'm certainly grateful to them for that. What I didn't anticipate is the way in which it would change my life. I did anticipate that I would get a lot more invitations to give talks and that I would have to manage my schedule in a different way. What I didn't imagine was that I would get to meet people who are actually famous. People often tell me, oh, you're a Nobel laureate, you're famous. No. If you were to go downtown College Park and ask people if they'd heard of Bill Phillips, unless a bunch of physicists happened to be walking by, you would ask 100 people and no one would have heard of me. But I've actually met famous people. I had dinner one night with the President of the United States. So that's kind of heady stuff. It's not the sort of thing that a physicist expects to do.
That's great. So, so we'll move on to some discussion of quantum, and thank you for talking about that for a little bit at the beginning. You know, a lot of people are investing heavily in the next quantum revolution, but can you talk to us a little bit about why it's such a big deal, and how is it going to affect everyday life and how we do business?
Yeah. Well, first of all, let's talk about this idea of a second quantum revolution. We've undergone an amazing quantum revolution in the 20th century. Today, even though a lot of people don't really think about it, almost everything that is part of our modern technological life is made possible because of quantum mechanics. We wouldn't be doing what we're doing right now if it weren't for the fact that there are computer chips inside our devices that rely on quantum mechanics to work. And we've become really comfortable with that kind of technology, even though we don't necessarily understand the details of how it works. But in the 21st century, we have begun to use, both to recognize the importance of it and to use the technology associated with aspects of quantum mechanics which really have not been part of that 20th century revolution. And we'll talk about that, I think, a little bit more as we go on. But what has this done for us? It's given us an entree into a different kind of quantum technology, a different kind of quantum reality, so to speak. Things like quantum computers that can tackle problems that are essentially impossible for even the most powerful ordinary computers of the sort that we use every day. Quantum sensors that will be able to detect things at such low levels that no ordinary detector would be able to do that. These kinds of things are opening up. Quantum cryptography that will allow people to share secrets in ways that no numerical attack is going to be able to compromise. In other words, codes that cannot be broken even by the most powerful computers, even quantum computers, wouldn't be able to break the codes that could be established using quantum cryptography. So this sort of second quantum revolution is both opening up really new things, but one of the things that's most delicious about it is that it uses the features of quantum mechanics that are the most weird. And that's one of the things that I like about it so much. Quantum mechanics is, at its heart, really weird. And we haven't really started to use the weird properties with all of our 20th century technology. But the 21st century technology is really going to get down into that weirdness. We often say what we're doing now is putting the weirdness to work. And I just love that.
I love that too. And now that you've talked a little bit about the promise of quantum, I am going to let you get into the weirdness here a little bit and tell us exactly, you know, why is quantum so different? And we do have a very broad audience here. It looks like a lot of people are just curious about quantum, but I know I've seen you give so many talks and you make it very accessible. So, so why don't you tell us something about quantum?
Great. Okay. So first, let's get rid of the first quantum revolution. What did that have to do with? It had to do, at least in large part, with the recognition that everything is both a particle and a wave at the same time. So what do I mean by that? Okay, people knew by the beginning of the 20th century that there were things called electrons. And an electron is a small particle. We can measure its mass, we can measure its charge. And then what quantum mechanics taught us was that we should also think of this thing as a wave. Now, how can that be? What is it that's waving? The fact is, even now, 100 years, almost 100 years after this concept came into being, I cannot answer that question, what it is that's waving. If you give me a water wave, I can tell you what's waving. You know, it's the surface of the water. If you give me an electrical wave, the thing that's broadcasting what we're doing here today. I can tell you what's waving. It's this electrical field. But if you ask me what is waving for an electron, I'm going to answer, it's the probability amplitude. And there's nothing actually reality that doesn't connect to that probability amplitude. So this is really already getting a little bit weird, but it gets a lot weirder than that. And this idea that everything's a particle and a wave becomes evident to us when we look at things like electrons. It's true of billiard balls too, but we never see it because the wavelength is so ridiculously short. But the wavelength of an electron in an atom is equal to the size of the atom. And therefore, you'd better take that into account. And taking that into account led to all the wonderful things we have in the 21st century. Okay, I mean the 20th century. Now, what's different about the 21st century? Well, first of all, it's not something we discovered in the 21st century. It's things that people already knew in the 20th century, that something can be in two places at the same time. Now, we often say, you know, when we're busy, well, I can't be in two places at the same time, but an electron can. How is that possible? Well, again, nearly 100 years after this idea was understood, I cannot answer that question of how that's possible. It's part of what about the way the world works at the level of atoms and electrons. We routinely in the laboratory have situations where we put atoms here and the same atom is also here. And you say, you know, how can that be? And I can't tell you how that can be, but I can tell you what it means. What it means is that when we measure, whether it's here or here, we'll get one of those answers. But it also means that before I do that, I cannot, even in principle, tell you which one it's going to be in. And if you were to imagine that, oh, it's just in one or the other and I just don't know, that would be wrong. And we can do experiments to prove that that idea is wrong. Now, if that doesn't make your head spin, then you're not thinking about it carefully enough, because this is just totally weird. But the second quantum revolution is going to make really fundamental use of that. But it gets even weirder with a phenomenon that we call entanglement. So let's say that one of the things we're going to measure is an electron. Now, an electron spins, and as a result, it makes a magnetic field, and that magnetic field points in a certain direction, like the direction of my thumb, okay? And according to this idea of superposition, I can make an electron so that it's spinning this way with the magnetic field pointing up, or spinning this way with the magnetic field pointing down, or both at the same time. Now, if I measure it, I'll find either this or this. No way of knowing beforehand which is going to be the result. Now let's have another electron. It also could be pointing up or down. Now here's the really weird part. I can entangle these two electrons so that the fate, when measured, of this electron is tied to the fate of this one. If I measure this one, I get up or down, and I don't know which beforehand. If I measure this one, I get up or down, and I don't know which beforehand. But if I could entangle them in such a way that if I measure this one to be up, this one's going to be up for sure, even though they don't talk to each other. How can that be? It goes against all of our notions of what it means to be real in this world. What it means is that the property of this electron doesn't really exist until I measure it, and that the properties of the universe are not local. That is, I can't describe the universe by saying what happens here to this electron. I have to include what happens with this electron over here that could be a universe away, but still in this funny way affects what's going on here. Einstein was so offended by this idea that he derided it as being spooky action at a distance. And he didn't like it at all, but it's one of those rare occasions when Einstein was wrong. This is really the way the world works. And what we're doing in the second quantum revolution is putting these kinds of weird features to work.
So that was awesome. So can you tell us a little bit about, maybe quantum computing is something a lot of people have heard about. So how would all of these things work in a quantum computer, and what is computing in a quantum computer like the computer I use now, or is it going to be something completely different?
And the answer is yes. It's going to be a little bit like the computers that we have now, and it's going to be a lot different. So one of the things about the computers that we have now is that the information is stored as bits. We all understand about bits. Bits can be either 0 or 1. What does that mean? It means that there's some physical thing inside your computer that is in one state or the other. Maybe it's a transistor in a semiconductor memory or processor that is turned on or off. Maybe it's a place in your magnetic disk that is magnetized one way or another. Maybe it's a spot on your DVD that is burned or not burned. So that's how digital information works. Something is in one state or another, burned or not burned. And the power of it is that it's very clear whether it's burned or not burned. It's very clear whether the transistor is on or off. And so we don't make mistakes. And in the one chance in a trillion that we make a mistake, we have ways of fixing those things, okay? In a quantum computer, information is going to be stored in bits that we call quantum bits, or qubits for short. And the idea is that you use some quantum object like an electron. Now, none of the ideas really use electrons, but since we talked about electrons before, let's stick with that. So the electron could be spinning this way and pointing up, or it could be pointing down. That's 2 states. Let me call this 1, let me call that 0, and now I've got a qubit. And now, the weird thing is that this qubit could be both 0 and 1 at the same time. Something you want to avoid in your usual computer, not knowing whether it's 0 or 1 is something you never want to have in your classical computer, but it's the power of the quantum computer. Now, you might say, boy, that sounds really bad because I never know what I got. But that's where the power lies. But the real beauty is that there's also entanglement, this other weird feature. And it's when I have a whole lot of qubits and they're entangled that I really get to see the power. So let's think how this works. Unfortunately, I don't have quite enough hands. Let's say that I've got 1 qubit, 2 possible states, 1 and 0, okay? Let's say that I've got 2 qubits. Now I got 4 possible states. This one, that one, that one, and that one, okay? Now imagine that I had 3. There would be 8 possible states. The number of possible states is equal to 2 raised to the power of the number of qubits that I have. Imagine that I had 300 qubits. Now 300 is not a very large number. You've got a terabyte of memory in your laptop. So 300 is a tiny number. Yeah. The number of different states that those bits could be in is larger than the number of particles in the universe. There's something like 10 to the 80th particles in the universe, a number that's so big that it's unimaginable. And yet the number of possible states that I could have with 300 qubits is bigger than that number. Mm. Now that would be true if they were classical qubits too, but here's the point. They can be in all those states at the same time because of this idea of superposition. And that general state is entangled, which is why I brought up the idea of entanglement. So that means that if the computer processes that information in that highly entangled state, it's processing many, many different numbers at the same time. And if you're clever, and I'm not, but there are computer scientists who understand quantum mechanics who are clever, you can design an algorithm that is a process, a computer program that can do things that classical computers cannot because of this power of having an exponentially large number of different states. And when I say exponentially large, what I mean is something that is 2 to the exponent of the number of qubits. A lot of people, when they say exponentially large, they just mean really, really big. I don't mean that. I mean something that depends upon an exponent of the number of qubits that I've got. And that exponential size of the quantum computer's ability to process is the thing that gives it so much power.
So it's powerful and faster?
Yeah, now faster is a really interesting question because current computers are really, really fast in the sense that they do lots and lots of operations per second. Probably our quantum computers are not going to be that fast. One of the reasons is that the physics that underlies those computers is just not that fast. But another reason is that for every quantum computer operation that I do, I'm going to have to do a bundle of classical computer operations. So I'm never going to run the quantum computer faster than the fastest classical computers. But that's not the point. The point is that what the quantum computer is doing is so powerful that even though it's doing it somewhat slower than the classical computer, it still beats the classical computer, or we hope that it will when we do the right things. There have already been demonstrations of problems that the quantum computer, even the sort of baby quantum computers that we have today, can do faster than any classical computer. The only trouble is that nobody cares about that problem. But it's not going to be long before we have quantum computers that are doing problems that we actually care about, that it does faster than any classical computer could do.
Well, another thing that people have been paying attention to is this idea that once you have the key to quantum science and technology, that you can then break all of the encryption that we know about now. And so everybody's going to be able to hack our emails and e-commerce, and all the classified secrets will get out, and the world order will be different. So can you put that in perspective and tell us if that's true?
So the idea that a quantum computer could break all codes, not quite true. It could break a large class of codes that people use routinely. So for example, when you buy something online and you put in your credit card number, you can be sure that some hacker who happens to intercept that message that you're sending to the online seller, you can be sure that that hacker is not going to get your credit card number, because there's an encryption process that happens, all done in the background, so we don't even notice it. But that encryption process involves the seller sending your computer a number. And that number is the product of two prime numbers. Now, prime numbers are just integers that are that don't have any factors. No, you can't multiply two other numbers together to make that number. So for example, 7, you can only multiply 1 and 7 together, right? 7 is a prime number. But 7 times 6 is, 42. It's not a prime number. Okay, so what they're going to do is they're going to send you a big number that is the product of two prime numbers. Now, your computer is going to take that number, do a bunch of computations on it, on your credit card number, and send it back. And the person who sent you the thing is going to easily decrypt that because of the fact that they know what the factors are. But it's almost impossible to figure out what the factors are because it's easy to multiply two numbers together. It's very hard to factor a number. And that asymmetry makes it possible to make encryption easy and make decryption hard. So the fact that multiplication is easy, factoring is hard, is the thing that makes this thing that we call public key encryption work. Now, the problem is that we have a computer algorithm, a quantum computer algorithm that can factor numbers. There is no classical algorithm that can factor numbers efficiently. The time required to factor a number with a classical computer grows exponentially with the number of digits in the number. It actually goes like the cube root, but it doesn't matter. It's still exponential, okay? So, but there's an algorithm invented by a genius named Peter Shor that can factor numbers in a time that only grows like the third power of the number of digits. So that's called an easy problem in computer science, where something that grows exponentially is called a hard problem. So you've turned a hard problem into an easy problem by changing the hardware on which you do the calculation. That's in itself astounding, but it's had this immense effect on things. Now, what it means is all these kinds of transactions where people use public key encryption will now be subject, now, not yet now, because we don't have a quantum computer that can do this yet, but people are hoping that we will in the future. If we do, then all those things will be open and can be decrypted. Now, nobody cares about your credit card. I'm sorry, you don't have enough money. But when it comes to things like diplomatic secrets, then it makes it really important. And for example, people are, I understand, recording these transactions today. You know, they're spying on people and recording these transactions in the hopes that sometime in the future they're going to be able to break these codes. And that could be really bad for the people who spent a lot of time making sure that these things were secure. But here's the beauty. Quantum mechanics comes to the rescue, because it's only that kind of encryption that's going to be in danger. There's a thing called a one-time pad. This is the kind of thing you see in spy movies. You know, somebody takes a code book, puts it in a briefcase, handcuffs it to their wrist, and carries it someplace else where somebody needs that code book. Now, that is absolutely secure as long as nobody intercepts the courier, steals the code book, or, you know, offers him a whole lot of money to bribe him, whatever, which still happens, of course. But that's a completely secure way of doing it. As long as you don't reuse the code book, then it's perfect. The key thing is that we can send a code book via a quantum channel and be sure that nobody has intercepted it. Mm. And we can generate the code book remotely then, be sure that it's not compromised, and then we have a one-time pad that we can use with perfect security. So quantum gives and quantum takes away.
That's fascinating. That's really fascinating, and a little bit makes us all think about the future and what that's going to look like once quantum technologies and science take over. Mm-hmm. So, you know, when you talked about, so I want to shift from quantum computing to the quantum internet. So the Department of Energy just made a big investment in quantum internet, and they're announcing nodes that they want to have all over the United States. Can you talk about what that means? What is a quantum internet?
Yeah, well, I don't think that the quantum internet is going to be very much like the internet that's allowing us to talk with each other. We're not going to be looking at quantum cat videos, or at least not anytime soon. The quantum internet is going to be a network of nodes and communication links that allows us to transmit quantum information. So for example, I was talking about quantum cryptography and quantum key distribution, this idea that we could transmit a code book. That's one of the things the quantum internet would allow us to do. The idea of an internet would be that you have more than two nodes. I mean, if I just got two people and a line between them, that's just communication. A network is something more complex, and that's what people mean when they say a quantum internet. And sometimes you want to share secrets between more than two people, and there are protocols for allowing that to be done in a way that prevents some other listener from getting that information. So that's one of the things that the quantum internet could be used for. It could link up quantum computers. It could be that you can't do everything you want to do on one quantum computer, and so you need a way of connecting to some other quantum computer, but you've got to get the quantum information over there, so you're going to need a quantum channel to do that. The quantum internet might be able to hook up a number of quantum sensors in a way that makes them more powerful, a way that will entangle them, to use that term that we've introduced before, and therefore make them more powerful as sensors. So perhaps such entangled sensors would be able to detect seismic activity, precursors of earthquakes, for example, more sensitively than just a single detector, or even more sensitively than a number of detectors that were connected in a way that wasn't quantum. So these are the kinds of things that we dream about that a quantum network might be able to do.
Can you talk a little bit more about sensors, quantum sensors, and what they are and what they're used for?
So let's imagine that I've got some quantum mechanical object that is making some kind of a measurement. One of the things I love best is clocks. We've been using atomic clocks since the middle of the 20th century, and they're a fundamentally quantum device. But now in the 21st century, we're starting to use this the second quantum revolution to change the nature of these atomic clocks. So let's talk about atomic clocks for a moment. Let's say that I get rid of all of the ordinary sources of what we call noise, the things that mess up the operation of an atomic clock. And this goes for any sensor. It might be something that's measuring magnetic fields. It might be something that's measuring intensity of light. There could be any number of things. And I've gotten rid of all of the, quote, ordinary forms of noise. What would that be for an atomic clock? Well, it might be the fact that there's some vibration, and that vibration changes something in the atomic clock. It might be that there's a stray magnetic field, that is, a car drives by, and the magnetization from that car changes the ticking frequency of the atomic clock a little bit. Or the radiation from the room might change a little bit, and that would shift the frequency of the clock. Let's say I get rid of all of that, then I'm still left with the noise that quantum mechanics demands. The quantum uncertainty principle tells me I can never measure some quantity better than a certain amount. In fact, what it tells me is there are two matched quantities. So for example, frequency, let's say I want to measure frequency, the matched quantity is time. I can't measure the two things simultaneously as well as I want. There's always, if I've got a certain amount of time to make a measurement, I just can't measure the frequency better than a certain amount that's given by the uncertainty principle. Now, with an atomic clock, the thing that's going to limit us is that I'm going to have this, some kind of an atom, and it's going to be, let's say, rotating. Its magnetic field, let's say, is rotating like that, and the rate at which it rotates is the ticking frequency of the atomic clock. Well, how am I going to determine that? I'm going to measure where it is at some time, but it's in a superposition state. So when I measure it, I get it. It's random what I get. Well, if I get a whole bunch of these together, then that randomness averages out, and I get a pretty good measure of where it is. And the more atoms that I have, the better off I'll be. And but there's always a limit based on the number of atoms. Now, here's where the magic comes in. If I entangle those atoms, I can do better by an extra factor of the square root of the number of atoms. Now, that may not sound like very much, but if I've got 10 atoms and I do this to them, then it means I get a better answer than if I'd waited 10 times longer. And that could be a big deal, because if the amount that it takes me to make the measurement is an hour, then 10 hours is a big deal, right? And that was just with 10 atoms. I mean, what if it was 100 atoms or 1,000 atoms? And our colleague Junyi out in Boulder, in the NIST laboratories out in Boulder, is doing exactly this with an atomic clock. So this is an example of how the power of the second quantum revolution, this idea of superposition and especially of entanglement, is going to make a sensor more powerful even after you've gotten rid of all the ordinary things that will mess up the operation of the sensor. You can still work on the quantum mechanical things. You can not really beat the uncertainty principle, but you can cheat the uncertainty principle a little bit by putting the uncertainty into something you don't care about and measuring the quantity you do care about better. So, so this is one of the things that we can do with sensors, and we can apply that same idea to, for example, LIGO is one of the best examples of this because it's happening right now. They have these huge interferometers. Basically what they're trying to do is measure the position of a mirror, and that mirror changes its position a really tiny amount, like a fraction of the size of the nucleus of an atom when a gravity wave goes by. And you want to determine the position of that mirror. Well, what limits how well you can determine the position of that mirror? The number of photons, the number of particles of light that you bounce off that mirror to measure its position is the thing that limits how good a measurement you can make. But you can only put so many photons on there because after a while you burn up the mirror. So what they finally did was they said, okay, we got rid of everything else. Now we got to work on the quantum mechanics. And so they did a process that we call squeezing. It's sort of like entangling the various photons in the light to improve the sensitivity of LIGO by something very modest, a factor of 2. But that means you can look out further into the universe, and you've got more objects that are in your field of view now. And so you can see more events. And every month, we're hearing about new amazing things that happen from LIGO. And in part, this is because they're taking advantage of this second quantum revolution. And so we're thinking, dreaming about applying this to other kinds of sensors, magnetic field sensors, light sensors, things that might be useful for detecting things that are below the surface of the Earth if we're prospecting for something, or detecting threats at some distance in a military operation. So all kinds of things are being imagined, and this is going to be part of the second quantum revolution.
Well, when you talk about those processes and quantum computing and quantum sensing, it just sounds like you need incredibly precise control of your system and your atomic particles, your electrons. So can you talk to us a little bit about how realistic it is that we're going to be using quantum sensors and technologies soon? Because I understand that doing these kinds of experiments requires that you freeze things to a level even colder than space.
Yeah, absolutely. So it's not exactly a consumer product because today we require a whole room full of apparatus in order to achieve the kind of conditions that allows us to see these kinds of quantum properties. Plus, in order to make it useful that you have, say, a quantum sensor, you have to get rid of all the ordinary sources of noise, which are the things that usually compromise the performance of these things. So first, you have to be really, really good in that you've gotten your sensor so that it's working at the quantum limit, and then you have to beat that quantum limit. And this is not easy to do. Neither one of those things is easy to do, but we're doing it now in the laboratory. And the question is, when will this be something that we can use in the field? And what about using it as a consumer product? Are we all going to have quantum computers and be able to do things with our quantum computers at home that cannot be done with our laptops? Well, I'm not sure I have a good answer to that. It is going to be hard, but I think that it is going to happen. I don't think that it's going to be like fusion, where we say it's always 20 years in the future, and that's been true for the last 60 years. So I think we are going to get it, but you never know for sure. But the thing is, we've been making such wonderful progress that it really feels like this is something that's going to happen. LIGO already works. We already have small quantum computers. We're definitely going to have quantum networks. So some pieces of this quantum revolution are already happening, and it's pretty clear that other pieces are going to happen. Are we going to have a computer that can crack codes, that can compromise diplomatic secrets? Well, I used to say, and I still say, I think that's a 50-50 proposition. I think there's a 50% chance it's going to happen in 50 years. Now, some of my colleagues think I'm being a little bit too pessimistic. They would say 20 years, but still, it's a long way off. In 20 years, I'll be dead. So it doesn't really matter which of it comes out. I won't have to answer for it. But still, 20 years is not that far in the future. There are a lot of secrets that, even if they were revealed 20 years from now, could cause a lot of problems. But I think we're going to have quantum sensors. I think we're going to have atomic clocks that are have a quantum advantage, that are going to allow us to do things like geodesy. It turns out that this is really amazing. An atomic clock changes its ticking frequency by a part in 10 to the 18th. Think how small that is. A part in 10 to the 18th when you move it vertically by 1 centimeter. When I first came to NIST 42 years ago, the best clocks were good to a part in 10 to the 13, which was about enough to resolve the distance between Washington and Boulder, where they had the clock that could do that. Now in Boulder, they have a clock that is 5 orders of magnitude better and can, in fact, resolve something at 1 centimeter. And these new features are going to make it even better than that, so that people will be able to do geodesy, measuring the profile of the Earth via its gravitational potential at the level of sub-millimeters because of these advances that are being made in quantum sensing, and the kinds of things that new sensors for magnetic fields, doing magnetoencephalograms, for example, may become standard. All kinds of things that I think are really going to happen. Quantum computers that can crack codes, I don't know. But, you know, all of this is done with really sophisticated laboratory technology. It doesn't seem to me that this is ever going to be something that's going to be consumer products, that we're going to have it in the home. But then I remember that in the 1970s, there were people who said, no one is ever going to need a computer in their home. And look how wrong they were. And these were heads of companies that, of course, don't exist anymore because they didn't have the vision to understand that people would use computers in their home. So maybe I'm completely wrong. Maybe we will have these kinds of quantum devices in our homes. But right now, it's really hard to see.
You've given us a really good picture of what the future could be, Bill. So I want to switch gears a minute on the last question that I have for you and ask you, what's our competition? So I know the University of Maryland and NIST and many companies in the region, we are really strong at driving quantum innovation, but other regions, other countries are accelerating and investing big time, China, for instance. So
absolutely. So I mean, it's absolutely fantastic to be here. The Mid-Atlantic Quantum Alliance comprises a group of people who are really top-notch when it comes to quantum. The Joint Quantum Institute that you mentioned before is one of the best places in the world to do this sort of thing. But of course, there are other places. The Max Planck Institute for Quantum Optics is an amazing place. The Paris region has a quantum consortium that brings together some of the most amazing people in the world. And you mentioned China. They're pouring a lot of money into this second quantum revolution. They have established a quantum link with a satellite so that they can transmit quantum information from the Earth to the satellite and back. And what is this good for? Well, it demonstrates that you can do this and establish this kind of entanglement over really long distances, which is one of the things that we all believe to be true, but actually doing it is an important thing. So we have really a worldwide community of people who are working on this. I am so happy to be here in Maryland working on this because I just can't imagine a more exciting place to be, where there's so many people, experimentalists, theorists, startup companies. Just steps away from the Maryland campus, we have IonQ, where they're making quantum computers with ions. But the other point is we are part of a worldwide community. And, I think of this not so much that we're running a race to see who can get there first. We're building a barn, and we're all working together to make something that's going to be really fantastic and is going to make all of our lives better.
Well, thank you for that. And John, I'll turn it back to you and ask you if there are questions that people have wanted to ask. And
we have gotten a number of just really good questions. So some of them have agreed to go live, but before I bring them on, I think the first one, and one that we've gotten in the chat as well, is what effects do you think quantum computing will have on advancement of artificial intelligence?
Yeah, I have no idea is the simple answer. But let me just throw out a few things that people speculate about. Some people have speculated that human intelligence is somehow related to quantum phenomena beyond the idea that everything is quantum. I mean, chemistry is quantum, and so, you know, and our brains work via chemistry and physics, and that's all quantum phenomena. But the idea is that some people have speculated that there are features of the brain that rely on things like, well, we haven't even talked about quantum coherence, but quantum coherence is the thing that allows you to have superposition and entanglement. And people have speculated that this may be the thing that makes the brain work in some of the ways that it works. See, one of the things is that nobody's ever been able to figure out how is it that a bunch of neurons that work through chemistry and electrical impulses can lead to something that is self-aware and has what, for, you know, for all appearances appears to be free will. Okay, nobody understands that. And so some people have speculated that maybe there's some quantum features because, you know, quantum features make things so much more complicated that maybe that's sufficient. And then if you had a quantum technology that allowed you to have computers that operated on quantum principles, maybe then you could make something that mimicked the human brain in that way. I have no idea whether that's anywhere close to being the truth, but who knows, maybe.
Perfect. All right, so next up we have Martin Mortier. Hopefully I didn't mess that up. So Martin, I have allowed you to talk, so go ahead.
Yeah, hey, thanks, Professor Phillips. So thanks so much for your insights into the second quantum revolution and your examples of applied technology, which is very, very exciting. So one thing I noticed as well with this resurgence of mainstream people knowing about quantum physics is that there's a lot of, like I said, a resurgence of philosophy of trying to interpret the weirdness, right? So there's a weirdness aspect, like you said, where things are in a superposition of states. And then there's this measurement that kind of leaves you with one random state. And then people try to kind of make sense of that, right? And there's a lot of theories, obviously. One of, in particular, is this many worlds multiverse theory by Everett originally, and actually by Schrödinger, I guess, originally. And I was just wondering, how do you feel about these efforts of people to try to sometimes use classical systems to interpret this weirdness? And do you think it's a futile effort? Is it something that will lead to discoveries? Do you think some efforts are on the right track? I would love to hear your thoughts on that aspect of quantum physics.
Okay, well, this is a question that often comes up about interpretations of quantum mechanics. So let me, first of all, say something about interpretations of quantum mechanics. Usually, when we talk about such things, for example, many worlds, you know, there are other interpretations, consistent histories. The one that I prefer is called shut up and calculate. In other words, refuse to have an interpretation. We've got a perfectly good theory. It allows us to calculate the things that we need to know. And if I don't think about it too much, then I'm not going to get upset, and I'll still get just as good answers as if I did think about it carefully with respect to questions of interpretation. All these different interpretations always lead to the same result, okay? So I think what that tells us is that having these interpretations these different interpretations is not going to lead to something different, except in the following sense. It may give us a different perspective and allow us to think about a quantum problem in a different way because we've used a different interpretation of quantum mechanics. And that may turn out to be really powerful. But there's another point, and that is that some people have developed interpretations of quantum mechanics with some extra features. The idea that, you see, one of the big things about measurement is how do we go from having a superposition where something is in both states to a measurement in which it's obviously in one state? How does that happen? And there's no obvious answer to that question. We have to sort of put in an extra feature about measurement that it wasn't part of the original idea of quantum mechanics. Well, some people believe that there's something in nature that destroys the coherence that allows something to be in two states at the same time, and somehow reduces this quantum mechanical beast into a classical object that is in one state or the other rather than in both states at the same time. So this sometimes goes by the name of fundamental sources of decoherence. If that's true, things are going to behave differently. And it could very well be that a quantum computer, which must, if it's going to work really well, it must maintain coherence for a really long time. It may be that a quantum computer will be more sensitive to seeing whether something like that happens. There's another feature that sometimes people talk about, and that is that somehow there should be a limit to how much information there can be in the entire universe, limited by how much information could exist at the surface of the universe using something called the holographic principle. The idea that you should be able to determine everything that goes on interior to some surface by knowing everything that's going on the surface. And so make the surface at the edge of the visible universe and imagine how much information there is. And if you insist that that information be classical, and I don't know why you should, but if you did insist that that information be classical, then you won't have enough information to entangle a few hundred qubits. We certainly intend to entangle a few hundred qubits in the laboratory, and so we might be able to have something to say experimentally about that kind of hypothesis. So it would be really great if quantum computing and the whole second quantum revolution allows us to test things that really make different predictions about quantum mechanics. But they're not, in my opinion, going to allow us to choose between different interpretations of quantum mechanics, but it still might be that keeping in mind different interpretations of quantum mechanics will allow us to make progress along this whole great adventure that we're in right now.
Fantastic. Thank you so much, Bill. Unfortunately, I think we have run out of time. There were a bunch of additional questions that I would love to get to. So we may need to ask you to come back and do this again.
Yeah, and Bill, I just wanted to say what a pleasure it is talking to you in this forum today. Thank you so much for accepting our invitation to be here today. And I can't wait to be able to sit across with you and have tea again. But this was almost like that, with almost 200 people joining us. So thank you.
Well, it's been a pleasure to have this conversation with you, Laurie. There's so many cool things to talk about when it comes to quantum science and technology that there's no end to this discussion. We could go on and on.
Yes, thank you so much. And before everyone signs off, I just want to put in a plug for our next talk, which will be this Friday, I believe at 4:30. It'll be J.D. Dolney, who is the chief scientist for quantum at Booz Allen Hamilton, talking about some of the industry perspectives of how quantum computing is starting to evolve in the wild. So please go to the mqa.umd.edu website to get more information and register for that event. And thank you all so much again. It was a delightful discussion. I definitely learned a lot, and I am just very grateful. Thank you so much, Bill and Laurie.
You bet.
Thanks.
So long. Thanks a lot, Laurie.
Bye. Thank you.